Well, science has come a long way since then, and we have a whole theory of how everything came into being. And let's take it from the beginning and see what science teaches today. So how did life begin? Well, science teaches that this Earth originally was very different to what it is today. There was a volcanic activity. The atmosphere was totally different to what it is today. In fact, the atmosphere consisted of gases like methane, ammonia, hydrogen, water, these components. And a scientist by the name of Stanley Miller came along, and he simulated this atmosphere, passed some sparks through it, and then trapped whatever was formed at the bottom and analyzed it in a laboratory. And lo and behold, here were organic materials. And so he conjectured that originally on the planet, there could have been an organic soup with lots of organic molecules, which then fortuitously formed themselves over long periods of time into the molecules which are necessary for life, and then through processes eventually came together to form the first living organisms. Now that's all very nice and well, except that there are a number of problems with this. Firstly, the atmosphere would have to be one that excludes oxygen. Very important. So, the primitive Earth reducing atmosphere is supposed to have had hydrogen, ammonia, carbon dioxide, methane, nitrogen, and water. And where did these come from? Well, they stated from volcanic gases, although volcanic gases are also associated with carbon monoxide, sulfur dioxide, so it doesn't really quite fit, but nevertheless, if it had, however, been like the present atmosphere, which contains oxygen, then the evolution of molecules would have been impossible, because oxygen burns up everything. Oxygen would destroy everything as it developed through the process of oxidation. So all scientists agree it would have to have been a reducing atmosphere. Now, what did Haldane do? He passed sparks through such an atmosphere and then trapped whatever was formed and analyzed it. If he had left it there in the atmosphere for another cycle, then everything that would have formed would have been destroyed by the next process. So he had to have a trap. Would there have been a trap somewhere on the planet before? Probably not. But there's another problem. And that is the various molecules of life that had to form needed very different circumstances. For example, if you look at the amino acids, you have different amino acids, and each one of these amino acids has this NH2 group, this amino group over here. And this NH2 group had to, of course, be derived from this atmosphere, and it comes from the ammonia. But now, if you have ammonia in the atmosphere, then sugars don't form. So here is a big problem. Plus, you need a very acid environment in order for these to form, and then you would have to have only the right ones to form. And that would not happen, because when you pass these sparks through it, you get left-handed ones, you get right-handed ones, and you get all kinds of amino acids where the amino group is attached to any one of these carbons along the chain and not necessarily to that first carbon next to this group over here, which is the carboxyl group. And so, if you have just one wrong amino acid somewhere in a chain, everything is non-functional. So here's a major problem, that you needed the right circumstances, plus you needed mechanisms of selecting just those amino acids which are useful to life. One wrong one in there and you would have a problem. Plus, even if you get the amino acids, how do you get them to come together and join together? You need enzymes for that. That means you need a protein to make a protein. So who was first, the protein or the protein that makes the protein? See, it's a bit of a problem. The next problem is, if you want to have the building blocks of our DNA, what our genes are formed of, then you need totally different circumstances. For these to form, you have to take all the nitrogen out of the atmosphere, change it into a cyanide solution, multiply that by 10, dissolve it in the ocean, and then you can get these molecules. But then you wouldn't get anything else. If you're going to make these sugars, again, as we spoke about earlier, that you need in the DNA molecule, for example, like the ribose, well, then you're not allowed to have ammonia. If you don't have ammonia, you don't have amino acids. So you would have to have many planets in order to create these things. No wonder science is saying it's not possible here, so maybe it happened in space. You have a theory there which is called panspermia. Now, this DNA molecule is another amazing story of life. Even if you get all the building blocks to form, how would you get it to form a string containing all the information that you need for life? How would you get it to do that? It has never, ever been demonstrated in a laboratory. It needs a very complex enzyme system that will form these high-energy bonds that are locked into this molecule. And the probability of these molecules forming is so remote so that we could say they are non-existent. So let's have a look at what the probability would be, for example, of a bomb exploding under a pile of wood, going boom, and then falling down from the sky and forming this perfect, functional little house. What would the probability be? Well, the probability is very, very remote. Let's give it a very good probability, or a very poor one. In fact, it's even much worse than this. Let's say the probability is 1 in 10 to the power of 80. Now, what is that? That sounds like a very small figure. 10 to the power of 80 is what physics claims is the number of particles in the entire universe. Particles. That means not only atoms, but subparticles. Electrons, hadrons, quarks, neutrons, protons, in the entire universe. How many atoms in a pinhead? Billions and billions and billions and billions and billions and billions, right? So imagine how many atoms in the entire universe. It sounds mind-boggling, but it's only 10 to the power of 80. It's not a very big number when you look at it, but that is really a mind-boggling number, 10 with 80 zeros behind it. So that would be the probability. What would be the probability of a simple gene coming into existence by chance? Well, there are 3 nucleotides needed to code for 1 amino acid in a protein. And let's take a simple protein that has 100 amino acids. Your hemoglobin, for example, has 600 amino acids. So let's take a simple protein, 100 amino acids. You need 300 nucleotides in the right sequence. What's the probability of that happening by chance? Well, the probability is 10 to the power of 127. That is, unfortunately, boom! New York City has been established by a nuclear explosion.